Alright, so let's talk our way through your guys' answers for, what is this, 2.4 number 22? I'm supposed to come up with non-zero, real 2x2 matrices with facts. So the first one was supposed to be that a squared is negative I. So what did you guys come up with?
I got 1, -2, 1, -1.
Is that what you got too, Richard?
Yeah.
No shit. Is that what you got, Dan?
I got close. I got 1, -1, 2, -1.
That's what I got.
Okay, and you guys check these, and they work?
Yeah.
Yep.
What was your thought process? I'm always curious how these came about.
I was thinking that the first column you would have to make it add the first row to be equal to -1.
Okay, so when you take this column and multiply by this row, you need a -1.
Yeah.
Okay.
And then for the second part, you need to take the second column and then have it multiplied by the first row to equal 0 and the second row to equal -1.
Okay, so you were like, so the second column has to be perpendicular to the first row.
Yeah.
Okay.
Actually, the one that I did.
Sorry, this one's yours.
Yeah, that's okay then. I also thought that the first column would have to be multiplied by the second row to equal 0, so I made the first column as simple as possible, the second one as simple as possible to get that 0, and then the third one I kind of just guess and check from that basis.
Cool. I like that as simple as possible was used there. Who had the other one that's slightly simpler?
01.
So, this is the one I want to talk about because this is where I'm at with these. I always think about the geometry of this situation, right? So I want a map, right, that goes from R2 to R2, right, where I get negative what I started with, right? So I'm thinking this way. I'm like, okay, so I'm going to start with a vector x, y, right? I'm going to do some function a to that thing. I'm going to get to, I'm not sure, right? I'm going to do a again to it, and I should get to -x, -y, right? You guys see that? So I'm thinking to myself, okay, so I need to do this with a matrix, so I'm not allowed to do much here, really. And I'm like, okay, well, both things have to be negative in the end, right? So I could do something like, well, what if I make the first one negative and leave the second one alone? Oh, but if I do that again, I'll get +x and +y. Okay, crap. So, yeah, so I need to, like, exchange them. So, if I switch them and make one of them negative, and then the next time I'll switch them, and then the other one will get made negative. Okay, that'd work. Now I just need to write down a matrix that does that. You guys with me? Alternatively, you might have tried that kind of, like, to come up with this. You might have also tried a different strategy. Did anybody try a slightly different strategy and came up with this one? You don't have to think about the geometry here. You might be like, okay, look, I need to end up with an identity matrix, right? So you're like, okay, well, I know the identity matrix multiplies to itself, right? So maybe I'll try slapping a negative in here. Notice that's the first thing I tried, right? That makes the first coordinate negative. So then you're like, oh, well, that didn't quite work. Maybe I'll exchange a couple of things. Cool. What does this say about square roots? Good, there's not a unique square root, and worse than regular, right? In algebra land, there's plus or minus. Here, I have at least 3 of these. How many of them are there? I don't know. Probably a lot. Considering that these don't look very much like what I was thinking they would look like, there probably are more. Sage, when you did this with algebra,
I'd imagine that
yeah, there's probably infinitely many.
yeah.
So if you sit down and carefully write out the component-wise squaring, you can set each of the kind of equations you get equal to either -1 or 0 and solve, right? You guys with me on this? So don't square root matrices. Not bound for success. That's moral 1. What is the moral of the second piece? The second piece was find a couple non-zero matrices with BC equals 0. What do you got, Liam?
So I got -1, 1, 1, -1. And the second matrix was 4 of the same non-zero number.
So just 5.
Yep.
Okay.
I got -1, 1, -1, 1, and then just a bunch of ones.
I did his matrix.
Wait. Does that one work?
Should?
Seems like it does. That's weird.
I did his.
Does this work with any matrix filled the same way Leo's does?
Mine is different.
Actually, let me check that real quick.
So if I had like a matrix with, I don't know, A's in it, right? That gives me 0.
Yeah, that would still work.
That gives me 0. That gives me 0. Gives me 0. Oh yeah. Sure enough. Okay, you guys found a cool thing, right? You found like if C is any matrix with 4 of the same non-zero entries and B is either of these. Oh, that's cool.
The other one is just where the columns are switched.
Where the columns are switched.
On the second.
Oh, like these guys?
Yeah.
Yeah, I think this kind of indicates that any sort of arrangement of -1 and 1s in here would probably work out. What's going on there is that the rows here are perpendicular to the columns, right? You guys see that? Okay. Anybody come up with anything else?
I had -1, -1, 1, 1. And then for the second one, I had 1, 1, -1, -1.
1, 1.
-1, -1.
Oh, yeah. That does work.
Seems like. Okay.
Makes sense.
Okay.
I did a different one.
Okay, perfect. What did you get, Alex?
1 0 0 0
1 0. Wait. 0 0
and 0 0 0 1.
and 0 0 0 1. Okay, so let's talk about the geometry on this one real quick. That first thing, right? So I'm thinking about this as a composite function, right? You guys all with me on that? So which function are we doing first? Yeah, if we're applying BC to a vector x, right? If we're doing BCx, this is apply C to x first, then do B to the result. Right? The same way you do f of g of x, right? So C of x here, right? If I'm taking a vector xy and multiplying by C, what's the matrix C do geometrically?
Makes x 0 and leaves 1.
So if I apply this to a vector xy, I get just the y component and sitting in the same spot. You with me on that? So this thing is so special we have a name for matrices like this. These are called projection matrices. This one takes the real 2 by 2, right? So it takes the real numbers, x, y, and then when you apply the map C to this, you get just the y-axis. You guys see that? And the action that this thing uses is the same one that you guys saw in Calc 3. Right? It takes every point in the plane and pulls them directly to the x-axis. Or, sorry, the y-axis. You guys with me on that? What's the other matrix here? B. What does B do? Good. B is the projection onto the x-axis. So if you take a vector and you project it onto the y-axis, and then you project the result onto the x-axis, you're smashing this way, and then you're smashing this way, and you done smashed it all, so it's gone. You guys with me on that? That is going to be my cartoon for any matrix that's not invertible. I'm going to think about it as smashing something. You guys see that? There's a good reason for that. We'll get there in a couple of 3 or 4 days. But for right now, I just want you to have that little cartoon in your head. You guys good with that? What is the moral of all this crap about matrices BC equaling 0? Yes, there are a crap ton of them. And what is the usual rule for BC equals 0 in, like, algebra class?
One of them has to be 0.
Yeah. In algebra class, if you take two numbers, b times c, and you get 0, one of them has to be 0. Are you guys seeing how there's not a fucking 0 product rule here? There's just ain't one. No chance, no way, no how. Don't get fooled into thinking there is one. It's a really easy trap to fall into. You guys good with that? So, no square roots, no 0 product. I'm just taking algebra away from you. No square roots, no 0 product rules. They're functions, right? What about your other one there?
D equals negative D, or ED.
Yeah, so I need two matrices D and E, so that when I multiply D times E, I get the opposite of if I did them in the other order. How many of you guys came up with one of these? Yeah, this one is hard. What'd you get, Leah?
I got for A, negative 1, 0, 0, 1.
Okay.
And I got 0, negative 5, 5, 0.
0, negative 5, 5, 0.
Oh.
So that's D and E.
Yes.
Okay, so let's see. This one makes, well, I guess I should talk about this one first. This one swaps, multiplies by, scales by 5, and adds a negative to the y component, right? And then this one adds a negative to the x component. You guys see that? So if I swap and make y negative and then make x negative versus ED, which is make x negative, swap and make y negative. You guys see that? You guys see how I end up with an extra minus sign depending on which order I do this in? Because it's you swap first and then make negative, or make negative and then swap first. That's cool. Very nicely. I probably, this is maybe just a little bit more obvious if you swap 5s for 1s. But I dig it. Very cool. What does this kind of say?
Multiplication is the, what is it,
Commutative. Yeah, multiplication's not commutative. I kind of knew that anyway because they're functions. This one says a kind of weirder thing. They can like almost commute sometimes. This kind of varying versions of commutivity. This one would be called anti-commutivity. Right, you can swap the order, but it crops up a negative sign. That's a little bit like the cross product in Calc 3, right? You guys remember that one? Those of you who haven't had Calc 3 are like, huh? There's a thing that does this later. It's a surprise. Any questions on this? What did we learn? What did we learn?
What Ricky said.
Principally, the big takeaway from all of these is there isn't a zero product rule. Otherwise, algebra also doesn't work like you intend, like you're used to it working. Why? They're functions in multidimensional space. There's more like ways for them to go wacky. That sort of seems like it makes sense, right?
Yeah.